students, we will be moving to our second session for the day. We have with us Dr. Amrutraj Mannambet. He is a product manager, currently serving as a product manager, Proteomics Life Science Group of Biorad Laboratories, India. He has been serving Biorad Laboratories from 2010 to present. Before that, he was been working with the USV Private Limited Mumbai as an associate chemist, clinical research process lab. And then before that, he was also associated with CIPLA Mumbai as a training analytical process lab, and also he was working as a professional sales officer in Win Medical Care, Mumbai. He is graduated from, he has a PhD in chemistry from Institute of Chemical Technology, Mumbai University. He is a master's in management, marketing management from Jamnalal Bajaj Institute of Management Studies, Mumbai University. He has various fellowships like Junior Research Fellowship, TUIP under World Bank from 2006 to 2008. Senior Research Fellowship from TUIP 2008 to 2009, and a Senior Research Fellowship PepsiCo 2009 to 2010. Best Product Manager Life Science Group India 2013. Star Club Award Biorad India for 2011, 2012, 2016 and 2017. Star Club Elite Award Biorad India for 2013, 2014 and 2018. With this short introduction, I invite Dr. Amrutraj to deliver this lecture. The floor is yours.
Thank you. I'll just share my screen. I hope my screen has popped up.
Yes.
So, good morning to all. Today, thank you, sir, for inviting me and for presenting this lecture. I'm feeling quite motivated to give this lecture to budding students across the board, and it's a very novel thing which you have asked us to give me a lecture for. Without wasting much time, I'll just, this is my topic basically for the principles, instrumentation and application for HPLC, MS, GC, GCMS, all pertaining to chromatography. To start off the proceedings, as sir mentioned, I'm Amrutraj Mannambet. I'm the product manager in Biorad Laboratories. Okay, so before I start off, what is chromatography? I'll just brief you of the organization which I'm associated with. Biorad basically is an organization started off in 1950s back in the US Hercules, California region. It has both life science research as well as products in clinical diagnostic. Just like we go for, your parents might be going for your diabetic testing, HbA1c. 8 or 9 after the 10 times they would be done on a Biorad instrument. In life science, basically whatever companies like in, for example, based out of Gujarat, be it Zydus, be it Cadila, be it Intas, they use our instruments on day-in-day basis, day in, day out, for creating products which are based on the biomolecules. It's a family-run business, more than 1 million customers globally, in presence of around 150 countries, and we are a 2.5 billion annual revenue, to say the least. The main motto for Biorad is advancing scientific discoveries and improving lives in multiple phases. Going forward. So we have offices, R&D centers spread across the globe. Our main center is in US, California. Our main center is in US, California. We have R&D centers across Europe, across Asia Pacific, and offices spread across more than 150 countries. And we are an ISO 9001 certified company with multiple R&D centers, and with Asia Pacific contributing more than 20% of the revenues to the global kitty. Just to say the least, what are the products which we have? In life science, where I am part of, we have products for biochromatography, for DNA amplification. You might have heard in the last 2-3 years, all of you getting tested with RT-PCR for COVID, non-COVID. We were the pioneers in partnering with ICMR and various state governments, providing real-time PCRs and solutions for having this tested on a day-in-day-out basis. Electrophoresis, gel imaging systems, and protein assays. In diagnostic, as I told, we have multiple instruments for monitoring either the thalassemia or HbA1c or HIV testing, and lot of products, instruments, as well as kits based on chromatography for monitoring the patient healthcare, and as well as a new product which group which BIIS has introduced is digital biology. It's an upcoming technology focusing on the third generation of digital PCR and providing solutions in the space of oncology, wastewater treatment. There are many benefits, having rare gene mutation detected, those sort of things. Going forward, jumping into chromatography, may I ask, has anybody heard of chromatography on a day-to-day basis, or have anybody come across any platforms? Okay, so if not, how does chromatography impact on a day-to-day basis? Now, chromatography as a technique, maybe from the audience perspective or from the participants perspective, you may have come across or you may have not come across. But how does it impact on our day-to-day basis? Chromatography is part and parcel of our daily life, be it whatever space. Example, the few examples which I've kept across is creating vaccines. Now, these vaccines are manufactured in bulk, huge quantities, thousands of liters. How are they manufactured? Part of the process includes chromatography. Chromatography as in separating out or separating the important component of the mixture which is used for injectables. For example, the COVID vaccine, which we are quite aware of in the last 2 years. So chromatography is an essential part of creating vaccines. Food testing, whether the food is edible or not, whether it has any organic acids which makes the food taste sour, are those compounds present? These are being tested again on a chromatographic instruments, be it big giants like the KFCs or McDonald's, when they issue or when they put out all the stuff in the market, or be it companies like PepsiCo for beverage testing, PepsiCo, Coca-Cola, whether they have any other component which gives different taste. So it has been used on a day-to-day basis. Drug testing, any major pharma company, you name it, they would have not one but multiple units of HPLC, LCMS, GCMS, you name it, they would be having multiple units. Why? Because whatever drug we take, be it a paracetamol, be it an aspirin, be it an antibiotic, whatever drugs come out, they need to check the purity of the drug. If there are impurities, the drug or the lot which has been manufactured is not released. So it is an integral part of any drug manufacturers to get this drug which are made in a huge quantity tested, and once these are tested and certified, these are released for subsequent consumptions of the population across the globe. Forensic testing is an interesting part. You might have come across various high-profile cases where, whether it be, I'll not name those, but high-profile cases where some of the samples being analyzed, be it a murder, be it some other criminal investigation, where these compounds, whether it be murder through poison will be injected, what are the poison content, these are again also be tested with the help of chromatography. It can be GCMS or it can be LCMS, to identify what is the compound or what is the poison being injected for which this is. So this has multiple dimensions where it has been used on a day-to-day basis. But yes, we may be aware, we may not be aware, but this is an integral part which takes care for chromatography. Going forward, chromatography is a century-old technique. The first chromatography was invented by a Russian botanist Mikhail. He uses this technique for, just a minute, in 1906 for removing or separating out different pigments of chlorophyll. Now, as a technique, this technique is essentially meant for separation of compounds and isolating each individual compound, first to find out the purity and also to find out different impurities which exist in the compound. So essentially, chromatography being a separation technique for multiple, it can be pharma, it can be biopharma, it can be food, it can be things. But yes, it's a separation technique, and it's a century old, more than century old, from where it was invented and conceptualized. Now, by definition, by International Union of IUPAC definition, chromatography is a physical method of separation between components to be separated. That is, you can see over here, it's a mixture of red, yellow, and blue dots. These dots represents 3 different components of different sizes and are distributed between 2 phases. Now, what are these 2 phases? One phase being stationary phase, while the other being a moving, which can be termed as a mobile phase. Excuse me. Now, the stationary phases are nothing but the resins packed in the column. You might have come across steel columns where there are columns inside. And the columns are packed with resins. These are small particles, as small as 1.5 to 4.6 micron used in HPLC. So that becomes my stationary phase. And your other phase, basically, it can be the liquid in liquid chromatography. That is the mobile phase, or it can be gas in gas chromatography. So that either the liquid or the gas, basically becomes the mobile phase, which is a definite direction, right? So this is the basic concept. You have the separated or the mixture of compounds, you have the stationary phase, you have the mobile phase, and there is a distribution between the stationary and the mobile phase, right? And depending upon how the distribution is, the compounds elute accordingly. Some elutes faster, some elutes a bit later. Now, what are basically the common features which you use or which are employed in the chromatography? The common feature are, it is 2 immiscible phases are in contact with each other. As mentioned earlier, it is a stationary phase and other being the mobile phase. So these are not miscible. Just like if you mix salt in water, it mixes, right? So it is a miscible. So, but if you put some pebbles in water, it does not mix. So basically, it's like a 2 immiscible phases. It does not dissolve or it does not get mixed. So are in contact with each other. Like the mobile phase is in contact with your stationary phase. Mobile phase being either the liquid or the gas. Stationary phase being the resins packed in the column. Now the sample, that is the compounds which are to be separated, undergoes repeated interactions with these 2 phases, that is the stationary and the mobile phase. And depending upon the interaction, whether it's a very strong interaction or whether with a very mild interaction. Again, these interactions depend on the physical as well as the chemical properties of the compounds and also the mobile phases as well. So the interactions, based on these interactions, if the compound interacting more with mobile phase, that is the liquid or gas, it will migrate faster. So what does it mean? So it will come out of the column first, and the compound interacting more with the stationary phase will migrate later, so that it will come late. That means the compound which is interacting more will come at the later part or the last part of it. So this differential movement of compound, and that is the interaction between the compound and the mobile phase, this is the responsible for the ultimate separation for the compounds. And that is where we are interested in separating those compounds and analyzing and also isolating. Analyzing in HPLCs, isolating if you go to bigger scale chromatography, just like I mentioned, creating vaccines. I want to isolate a lot of liters of vaccine or the compound of interest to be mass circulated. So these are the important criteria if you remember and if you want to going forward of chromatography. A differential movement of compounds between the stationary and the mobile phase, which results in ultimate resolution. Now, what are the different types of chromatography? Now, firstly, we talk about basis on the mobile phase. Now, basis on the mobile phase, it can be either a liquid chromatography or a gas chromatography. Now, it's just as I don't have to explain in detail, it basically the physical state of the mobile phase. Now, basis on the scale of operation, that is a second. Now, if I'm wanting to just analyze and let the compounds go to the waste, it's basically an analytical scale. But if I want to go for a preparatory and production scale, it can be vaccines, it can be monoclonal antibodies. We heard about for treating COVID, there are concoction of monoclonal antibodies being treated. So those are production level scale of operation. So it can be based on the scale of operation as well. Certain technique on the basis of adsorption. These are mainly some compounds bind, which is called the compound of interest, which if it binds, it is called positive chromatography. And it's vice versa. If the compound of interest which doesn't bind in at the start and it comes out, it is called the negative chromatography. Again, these are all classifications depending upon the compound of interest, depending upon the scale of operations, we could decide how to go about it, whether it be the positive or negative. Elution also will be based on how we need to separate out for a single product. It can be isochrotic. Isochrotic meaning throughout the entire run, it can be the run can be for 60 minutes, it can be for 6 hours as well. The composition of the mobile phases remains the same. Whereas in gradient, there is a change in composition, which can be a linear gradient. That is, when you go flat up, it can be called a linear gradient, or it can be step gradient, just like we take the steps on the stairs. You climb up and go steady, climb up and go steady. So it can be based on that as well. So this is how the chromatography can be classified in multiple aspects based on the mobile phases or the elution or the scale of operation or even the adsorption. But yes, it is important to understand where we are or what are the scales of operation which you are doing and how we can substantiate it further. Now, this is a graph, quite busy slide and lot of notations which is there. But this is one graph which will be coming across quite frequent if you are going ahead and dealing with chromatography in one form or the other, be it a liquid, be it a gas, in one form or the other, you will be coming across this graph quite often. and it is and there these are some of the terminologies which are used on a day-to-day basis. Most commonly the terminologies used are, for example, the retention time. So what is the retention time? Is the time at which my compounds are eluted out. If you recollect a couple of slides earlier, I mentioned the compounds which are interacting the least comes out first, and the compounds which are interacting the most comes out a bit later. So these are the retention times. This is basically a peak, the corrected wall, the peak as in the peak height, and this becomes my baseline. That is where the UV detected is stable. There is no compounds coming out or that. And this becomes my baseline separation. So each and every compounds are separated out clearly. In chromatography, it is also essential to develop a method where these are separated. If the compounds are not separated out for either the analysis part or for your preparative and productions part, you will not get a pure compound. So as there are number of methods and optimization which are employed to get this baseline separation. So once you get this baseline separation, for example, in an HPLC, then you can transfer, or then you can couple this method with an MS, because with MS for a pure peak, you'll get a corresponding M by Z, the mass to charge ratio for this. But if you are not having a optimized method, if you have injecting a mixture or not pure compound, you will get a multiple M by Z, thereby which may lead to different inference of the results. So hence the baseline separation is an essential part for chromatography which needs to be employed. There are methods which come as a default with lot of publications, lot of molecules been researched. There are few methods which needs to be developed at the user end, which is a part of the routine process. But yes, the retention times, the peak height, the peak width. What is the peak width? For example, this peak is a Gaussian peak. If your peaks are not sharp and Gaussian, and if it's just spread across, then also you need to work on that, or else it could be a suggestion, or it could be an observation that the column packing has gone bad, so it's a time to replace the column. So these are the small aspects which you infer when you look at a chromatogram and take decisions accordingly. Now if you go to automation, excuse me, I'll just have a second of it. Now, if you go to automation, be it a LCMS, be it a GC or GCMS, there are 2 or 3 important components of instrumentation for chromatography. This being the column, it can be for an HPLC, it can be a GC. I'm just showing a representation so that you get an idea of what I'm talking about. The first important aspect is an autosampler. For a HPLC or a GC, you require an autosampler which can hold vials and with automated sucking up and piercing the vial and taking up either 20 microliter or 30 microliter of sample and injecting into the column. So first component is an autosampler. The second component for any chromatography system is to pump to push in the solutions. Now pump basically is being employed for the liquid chromatography. But if you employ GC, it's nothing but the gas pressure with which the gas is being pushed onto the column. So in liquid, it becomes the pump, wherein gas, it becomes the gas pressure. If the gas pressure is there, you regulate the pressure and the flow so that the compounds being injected is passed through the solution, and there are multiple interactions, and then it gets separated out as shown over here. So once the compounds are separated, it's like a continuous process. I'm just showing one by one. Once these are separated, it is continuously being read through a detector. it can be UV, it can be conductivity, it can be pH, it can be refractive index, that's an RI, it can be fluorescence, it can be DAD, PAD, you name it. You have multiple instruments with multiple detectors. Depending upon what the column type is, what the samples being analyzed, the detectors can vary. But yes, after this, you have the detectors to analyze each individual chromatogram, which can be recorded on the slide which I showed a bit early, just one last slide. And after this, there are some processes, especially in preparatory and production scale, where you require a fraction collector. Because if there are certain applications, I want to isolate that compound or the compound of interest to maybe the study the structure, study the biological activity. Maybe in terms of in vaccines, I want to collect only a large amount. So you will require a fraction collector or a diverter valve. So these are essentially the basic components of chromatography systems. You have the auto sampler, you have the pump for liquid, you have the gas pressure for gas, and the detectors, and subsequently fraction collectors for few of the applications. So this becomes my backbone of the instrumentation for any instrument. There are multiple vendors in this space who gives solutions for HPLC and GC and LCMS and GCMS, but this becomes my background. You can have different types of LC. For example, you have something called a HPLC, that is high pressure. The pressures operated in this instrument is something with the range of 6,000 psi. The particle size of the resins in HPLC is, for example, 4.6 micron. That is less than your hair width. It is less than that. There is something, a newer generation of HPLCs, that is UPLC, that is ultra high pressure liquid chromatography. Even the pressures are much higher. The pressures are up to 10,000 to 12,000 psi, and the particle sizes are even smaller, that is 1.5 micron. So where does this pressure come from? Now, in liquid or gas, the pressure comes from the resistance. Resistance to what? Resistance to the flow rate by the stationary phase, which can be in the column. So there you generate the resistance and the pressure. So this pressures is nothing but the resistance to the flow rate being injected in the column. It can, so it depends on the particle size, it depends on the flow rate, that is 0.5 ml per minute or 1 ml per minute for liquid, or the gas pressures for your gas flow rate for your GC. So it all depends on the particle size and the type of instruments being employed for your HPLC or GC analysis. So going forward, like as I was mentioning, the different detector types, you have the refractive, ELS, and your conductivity, UV visible, fluorescence, and mass spectrometer. Again, mass is a combination you have attached to this LC, which is there, which is in itself is a huge instrument per se. Now, now we have looked about the instrumentation and the key components of HPLC or a chromatography system. Now we come to the column part of it. The column part, as in where actually the magic happens of separation, depending upon the type we choose in. Now here I want to emphasize the different types of chromatography resins basis, and this is how we employ different physicochemical characteristics of the compound. We try to exploit it and then try to separate according to this physicochemical properties. It can be gel filtration, it can be ion exchange, it can be hydrophobic, affinity, mixed mode, or reverse phase. So these are the different types. I'll not go into detail on each and every type, but these are the basic physicochemical properties on which we exploit, and we choose the column, as in the resins inside those columns, and the mobile phases changes accordingly. It is important to know what are the properties of the component which you are purifying, basis on which you can select this. You cannot go blind for having the purification. Hence, important to understand what are you purifying, what are the characteristics, and then selecting accordingly. So these are the most commonly used. Reverse phase is the most commonly used in your HPLCs, where it is coupled with either the MS on this. These are mainly used for your preparatory scale and production scale, especially for the biomolecules, where you go with the monoclonal antibodies or vaccines or therapeutics, biotherapeutics. These are the types or techniques used for your isolation, and reverse phase for your C18 and C28 columns. Now coming to GC or HPLC, what are these and where have been used? On the right side, you can see on top the HPLC used. On the bottom, you can see the GC. GC is depicted by, you can see over here, these are the different gases being injected. So these gases are connected downstairs or outside with the cylinder, and adequate pressure is being checked, being used. Again, irrespective of the GC or HPLC, both are separation techniques, has gained immense popularity over the past 5 decades. And why? Because of the applications it caters and giving a quantitative results for checking the purity, checking whether it is good or not, whether it's edible, whether it is injectable for your pharmaceutical, foods, life science perspective. If you go to gas chromatography, it is mainly employed for your volatile compounds or smaller compounds. It can be used for hydrocarbons, alcohols, aromatics, in pesticides, steroids, or fatty acids. So these are the industries which uses or employs GC on a day-to-day basis. You name it, for example, the IOCLs, the BPCLs. These are the instruments we have checking the hydrocarbon content, and they because basis on which it releases the batches or the containers which is there. So GC has been used for that. Even for food safety and environmental testing, GC has been used. So this becomes broadly where all the HPLC and GC can be used for different scales of operation. Now coming to mass spec, very important aspect which has added another dimension for an analytical technique, which is not only important to get pure, but also important to see and analyze what is the chemical substance or what are the structure by which we can the separated out we can elucidate the structure of the compounds. It is nothing but identifying gaseous ions. It is basically you require ions and it has been bombarded, and recording the M by Z, that is mass to charge ratios of the entire compound as a whole, and it is also been broken down to see what is the purity of those broken down radicals. And these are the Nobel laureates who has invented and made this technique popular, and they are the Nobel laureates for this mass spectroscopy per se as a technique. Now, when LC and GC is combined with mass spec, we call LCMS or GCMS. It is not only used to separate out, which is a part of LC, but also analyze and identify unknown peaks, which is a part of the MS part. So these two in combination is an absolute beautiful and a very powerful tool for any industry, because it not only helps you to separate out, but also helps you identify the unknown. And because that is the key aspect, whether the compounds separated are pure, if there are any impurities, there might be other M by Z ratios coming out, which may put a halt on the batch to be released for the public use. So these are a very important tool in combination of it. And most of the companies do have this technique in multiple quantities across board, in multiple departments, be it QC, be it analytical, be it product development as well. So they have these platforms for coming across this technique. Now, how this is steps involved in mass, as I told, in liquid and gas, there are 3 steps. Here you require, after the sample enters from the either the LC or the GC, you have an electron beam source. So this source basically is a heater which vaporizes a sample, because the sample can be in liquid or can be in gas basically. So you need to vaporize it. So once it gets vaporized, the stage 1 is basically the ionization, because you bombard with ions so that there is a charge to it. And because of this charge, and it gets accelerated in this field. So once it gets ionized, it gets accelerated, and then with the help of magnetic, it gets deflected onto the detectors, depending upon the size of the M by Z. And there are different, and this is how you record the M by Z of the compounds being separated out. So this is in short or in brief the 4 stages involved in mass spectroscopy or mass spectrometer: ionization, acceleration, deflection with the help of the magnets, and finally the detection. And this is how you look like. So this, the red part becomes my liquid chromatograph that is coming from either the LC or the GC, and this part, basically the 3rd dimension, becomes my mass. For example, for this peak, there are 2 masses available, which can be again seen M by Z ratios. For this peak, it is just 1 mass, and for this peak, it is just 1 peak. So for this, it can be broken down to 2 mass chromatograph, and this is how you try to elucidate not only the structure but also trying to find out what is the unknown peak coming out. Now, what are the different components of an mass spectrometer or MS? As I mentioned, the sample introduction, the gas phase wherein the source of gas is there, ion sorting. It depends basically to sort out the ions depending upon the charge, and a detection part of it, and finally the data system, which comes the output. Now there are various types of mass analyzers in the market, depending upon the complexity, the sample volumes, the mass analyzers are chosen accordingly. I'll not go into detail of each one of it because each one of it would require an hour of its own. But just to give you a brief of what all the analyzers are, briefly used are quadrupole, time of flight, it is also called TOF, magnetic sector analyzer, electrostatic, quadrupole, ion trap, and ion cyclotron. So these are the different types of mass analyzers in the market. Again, this can be coupled, these are coupled with an HPLC to give desired results accordingly. Now, coming to the instrumentation part, what are the components, as I showed just with the graph, but going forward, what are the components, and just as an instrumentation part, what all things are there? Now we have basically 2 buffers, 2 solvents or 2 mobile phases to put it. Now here we have a vacuum pump. Now vacuum pump is required because in organic solvents used in HPLC, you have oxygen dissolved, and if you have oxygen dissolved, you need to remove, and with the mixing of buffers or mobile phases, there may be some oxygen generated or bubbles generated. Now, to having that removed, and that may hamper your detection or your analysis. So hence, for doing that, we have something called a degasser. I just showed the pump part of it, but I'm showing in level down or level beneath to what all exact things are there. So a vacuum pump removes all the dissolved oxygen. It is also called as a degasser, which is coupled with a degasser, removing whatever dissolved oxygen or air bubble within it. After which there is a solvent mixing. There is an auto sampler connected, which is not shown over here, but again, assuming an auto sampler for injecting the samples. Then it goes to a pre-column. Certain columns are expensive. For example, it ranges up to 2 to 3 lakhs of the column. And to save that column, we have something called a pre-column or a guard column, just to save the precious column, so that this does not get damaged or faster, so that you have something called a guard column, just so that we can replace this, becomes an easy tool for replacing. And after the analytical, the detectors are there, and the recorder, nothing but the software on which the chromatograms are recorded. So the lab setups, this is how the lab setup looks like. On top, you have the HPLC, you have the preparative, as I told, in terms of preparative scales. You require a fraction culture. And on the bottom, if you see, these are production level scales. These, if you go to any vaccine manufacturing or any biopharma company, be it a Biocon, be it Reliance, you would invariably come across these platforms on production level. So again, lab setups with different liquid chromatography platforms in the scope. Now, if I come to the next part, that is the LC-MS, the first part which I explained for the LC, after the column separation, now it goes to an interface called the LC-MS interface, which have the ion source. As I mentioned in the earlier slides, you have the ion source for ionization, and then basically you have the acceleration part of it. And once you accelerate, basically, then you have the mass spectrometer for differentiating between the different ions, and then the detector part of it. Finally, the chromatogram, again, software based for most of the instruments for detecting the LC as well as MS chromatogram for that mixture of compounds. Again, real world examples. So on the left, basically you can see this becomes my LC, this becomes my MS. So this is something called a time of flight. So the ions, just to give you a brief, travels up and down, and it's basically there are multiple mirrors kept across. So depending upon the M/Z ratio, the heavier travels later, the lighter travels faster. So that becomes separated accordingly. This becomes my ion trap, to say the least. Again, this becomes the LC, and this becomes my ion trap. And this becomes, again, with the LC covered with a triple quad MS detector. So these are the various real world examples at the display, which I'm sure once you step into the private world, or even in terms of the academics, you'll come across this platform earlier rather than later. Now, coming to the GC, we looked upon the instrumentation for the liquid chromatography. Just a small change with GC is replacing the pumps with the gas, and we regulate with the pressure of the gas, which basically are inert. It can be helium, nitrogen. Those sort of gases are used for passing on the columns. Then we have some traps, so that any moisture or anything which can be not good for the column and the system per se, those traps are put so that anything coming out of the gas are trapped in the traps over here. Again, the auto sampler injection, the column, it has been HPLC and GC. Sometimes in GC, the columns are being heated up to 80 or 60 degrees, depending upon different columns and types. And then you have the detectors, and subsequently the chromatogram for the GC aspect. Same goes with GC coupled with MS. You have the MS detector, you have the GC, and you have the capillary column along with the auto sampler. So you have the capillary column oven, you have the fan, which is basically the oven part of it, which is placed inside this. You have the mass detectors, you have the auto sampler, we have auto injection. So this is how your real life example from the GCMS looks like over here. Now, if we go to application, as I mentioned at the start, from the forensics, it can be for drug use. Also, it can be used for, you remember, like a lot of the Olympic Games, Commonwealth Games, their blood and urine sample are also analyzed for checking if there are any steroids or any enhanced drug which the athlete has taken. So this can be used for that as well. Environmental testing, water and soil persistent organic pollutants, again, is one of the many applications which either the LC or the GC are coupled with MS are being used. Biopharmaceuticals, as I told, antibody drugs, vaccines, protein glycan analysis, various applications where LC is used. Food and beverages, food additives, sweeteners, pesticides, like the Coca-Cola, Pepsi's, the likes of McDonald's and KFC's, they also use LC and GC in their part of the QC analysis for releasing their batches. Pharmaceuticals, as I mentioned, your drugs, chiral drugs, your normal drugs are used. And also in terms of industrial, whether for industrial discharge, are there any compounds which are very carcinogenic for the before it is being released to the sea, so that the treatment can happen accordingly. So there are various applications, you name it, you have a lot of applications with this, and it is a technology or a technique which we can't evade and which can't escape. So somehow we are using chromatography not as a directly, but somehow chromatography being used in the products which we use on a daily basis. So with this, I thank you all for your kind attention for the talk. And basically the session is now open for any questions which are to be talked on. Yeah.
Thank you, Dr. Ramnath.
Yeah.
So the session is open for discussion. If you have any doubts, you can ask.
Yeah, Anjali Sharma mentioned BIIS website containing toolkits truly safe for undergraduates actually. Yeah, so Anjali, we have something called EDU or Education Division, Anjali. So it's like small kits, especially for your undergrads and in the class 2, +2. They're like, for example, isolating DNA from your cheek cells. How do you isolate DNA from your cheek cells? There are certain kits like biofuel, how to isolate biofuels. So BIIS being a pioneer in the domain which we are in, we also try to motivate young scientists and young students how science can be fun and beautiful to work with. So we have something called EDU, or the educational department, where we have small kits especially used in this platform. Yeah, so you can get in touch with us, so we can we have these kits which are available, which can be part of the curriculum for the undergrad and postgraduates. Yeah, so, apart from the Anjali has one more question. I have a question. Apart from the, I'll just read out the question. Apart from all the column chromatography that uses gravity as a major factor for separation, HPLC uses pressure to move the solvents. As a UV told in the talk, I'm confused. Isn't maintaining the pressure really troublesome? I have heard people facing problems for unstable pressure many times. So the question is, so is it really a thing, or do we have to have an automation for fixing pressure issues? So Anjali, right? So Anjali, now pressures are an inherent part of column chromatography. Now, as I told, pressure arises from resistance of the flow for the liquid with the help of either the stationary phase or the flow rate. In gravity also, we don't record the pressure because it is just gravity, like a burette. You fill in the resins and it comes out. And if the solvent is less in the reservoir, the flow rate will reduce, or the solvents will reduce. But if we go to an automation, every system has a limit of operation with respect to the pressure. As I told, in HPLC, the operating pressures are 6,000 psi. So it is quite high. There, I'm not sure whether, so these are the usual operating conditions under which you operate. So the rate limiting step for pressure is not the system per se, but what is the pressure which the column can tolerate. For example, if my system can tolerate a 6,000 psi, but if the column operating pressure is 3,000 psi, I will put a check mark on the software so that my system pressure will not go beyond 3,000 psi. Because if my system pressure goes beyond 3,000 psi, which may break the packing of the column. So it is essential to understand first the operating pressure of the system, second the operating pressure of the column, and then you accordingly select in the software what to put in. I hope I have answered your question.
Any other questions?
I'm sure you might have find this talk interesting. Please pass on any questions if you have now, or if you want to connect me later. We are more than eager to help budding researchers help out some questions. Over to you, sir.
Thank you so much for joining us today and elaborating the students regarding the HPLC, CCMS. Hope the students got a glimpse of the advanced instrumentation techniques, and in future they will make use of it. Thank you so much, Dr.
Thank you. So thank you all. Best luck for your future endeavors. Good luck. So I'll just disconnect, sir. Thank you.
Thank you.